The question of why there is a limit to how tightly we can focus, or what resolution we can get at an image, is one that is well studied in optics. Despite the obvious practical and theoretical difficulties in beating the diffraction limit, because the question is so important, it's one that we keep revisiting. Many of the discussions of limits to focusing are given in terms of diffraction, which is a well-known and much-studied approach. And in this reference, you can see a brief discussion and references on this topic. The idea of communications modes gives us another way of looking at and understanding this issue. Specifically, the idea of a sum rule on connection strengths, which is very fundamental and novel in this approach. This sum rule enforces limits quite generally. Here we will explore this sum rule further, giving a new and very general result for all wave systems. The communications mode approach gives us answers even when we are not working in the more conventional optical systems with large plane surfaces and lenses. For example, we can get meaningful results even when working with concentric spherical surfaces, a kind of system quite beyond diffraction models. There is also a specific observation that comes from numerical experiments that further reinforces the results of this communications mode approach. Specifically, beyond some simple and almost intuitive limit, we see that the coupling strengths of all subsequent communications modes fall very rapidly and apparently exponentially. This leads to the heuristic conclusion that trying to beat the diffraction limit gives only linear improvement at exponentially rising cost. So let's see how this works. When we consider all the communications modes in an example problem, such as this one between lines of sources and receivers, we find something quite surprising. Once we pass the number of channels we expect from conventional ideas of diffraction limits, the coupling strengths for any further communications modes fall off drastically and approximately exponentially. So here is what we've called the Paraxial heuristic number, but this also agrees with conventional diffraction models of the number of channels we should have in a system. But note that past this Paraxial heuristic number, here, the coupling strengths fall off very rapidly. Note this is an exponential scale here. On a linear scale, they've completely disappeared, and here we are down to 10 to the minus 8 in the coupling strength, essentially, once we've passed this Paraxial heuristic number. So linearly, it's quite obvious we don't have many more channels, and we see if we look exponentially or logarithmically that indeed the coupling strengths are falling off very drastically. This exponential fall-off past some characteristic number of channels appears to be common in many different situations and may even be almost universal. So here we're going to look at a problem. It's perhaps a slightly artificial one, but it's a problem that is not one that would be handled easily by conventional diffraction theories. The problem is one where we imagine having a spherical shell source, here of diameter 8 wavelengths, and a spherical shell receiver, here of diameter 24 wavelengths. So we can, if we like, imagine some dense set of source points on this inner spherical shell and a dense set of receiver points on the outer spherical shell. And here we're showing it for 3 different sizes of the inner spherical shell. Now, what we're showing here in this graph is basically the strength of the coupling relative to the coupling in the most strongly coupled mode for the communications modes for this problem. And we see a few things in this. We see actually a somewhat linear fall off in the coupling strength down to approximately some threshold here. And then after that, we see what is a sort of exponential fall off, an underlying exponential fall off. And here again, we see that on a logarithmic scale. For all 3 different sizes of these inner shells, we're seeing similar characteristic behavior. The exponential coupling strengths are falling off faster for the orange line here, which corresponds to the 8 lambda inner sphere, than they are for, say, the red line here, which corresponds to the 2 lambda inner sphere. So as I said, concentric spherical shell source and receiver spaces are not easily analysed by conventional diffraction limit theories, and they do not show paraxial degeneracy. Note that up to this characteristic number here, the coupling strengths are actually falling linearly. They're not constant up to some threshold. So this is unlike the case we saw with lines, or a similar case we would get for plane parallel surfaces. As I said, the coupling strengths here are tending to show an asymptotically linear fall-off up to some value here of the number of channels, which we're calling a spherical heuristic number. And we're just making this up here empirically, but here is the expression we have for it. And that actually corresponds to one mode for every square half wavelength on the inner sphere surface. And this makes some intuitive sense. After this linear fall-off, then the coupling amplitudes show, as we said, an exponential fall-off underlying the detailed behaviour. The coupling strengths have to fall off because of the sum rule, though that does not explain why this fall-off is apparently exponential, which is an intriguing point. The uniqueness of the communications modes and the exponential fall-off of coupling strengths explain why focusing past the diffraction limit is so hard. We only get linear improvement in resolution at exponentially increasing cost, for example, of the source amplitudes. And to see this in more detail, look at this reference here. So here is a numerical experiment to attempt to form a Gaussian beam, but at a width that is below the diffraction limit as conventionally interpreted. And this particular problem is set up just for lines of sources and lines of receiver points. So we're trying to have a line of sources configured in such a way that at the line of receivers, they generate a Gaussian beam. And the desired Gaussian beam amplitude at those receivers is given by these dots here, the red dots. Now, we can always figure out what are the source functions we should be using to try to generate a given beam at the receivers. It's relatively straightforward to do that. So we can calculate, first of all, what amplitudes we would need in the various communications modes in order to get this Gaussian beam at the receiver. So these red bars here are the amplitudes that we would need to have of the various communications modes in this problem if we were to generate the Gaussian beam. However, you can see that as we look at the higher mode numbers here, the amplitudes we would need at the source modes become gigantic. So if I only use 12 source modes, the first 12, which are more or less those that correspond to diffraction limits, then I would get this black curve at the receiving surface. And that only involves relatively moderate amplitudes of the source modes, as given by these grey bars here. So that's the first 12. We only need the odd ones in this particular case because it's a symmetric beam. If I try to get a curve that is closer than this black curve is to the desired red dots here, then I can increase the number of modes that I'm going to use. For example, I can increase to 16 modes. And if I increase to 16 modes, I then need to add in 2 more modes on the sources to try to do that. And you see the amplitudes at the source end are becoming quite large. That's because the coupling strengths for these additional modes I'm trying to add in are very small. They are basically past the conventional diffraction limit. And I get some improvement. I get this pink curve here, but not an awful lot of improvement. And if I try to do better, going up to 20 modes, I get the blue curve. But look at what's happening to the amplitudes of the sources for these 17th and 19th modes here. And note the scale. This is the modulus squared of the relative mode amplitude at the driving end, in this case. And by this time, for the 19th mode, we are having to have a source amplitude that may be of the order of 10 to the 4 times the general scale of those we were working with when we were below the diffraction limit. And if I try to go to 23 modes to do even better, then in principle I get this orange curve that is now getting fairly close to the red dots. But look at the amplitudes I'm having to use for the driving sources. Now I'm up to something of the order of 10 to the 8 for this one. So as I said, here we're trying to focus a Gaussian beam that is somewhat too small, for example, just past the diffraction limit. By adding more of the weakly coupled modes, we can make the Gaussian beam smaller than the nominal diffraction limit, but we require enormous source amplitudes. We obtain only approximately linear improvements in reduced spot size by adding more modes, but at exponential cost in the required source amplitudes. This is why subdiffraction focusing is essentially practically impossible. We can try again with another form. We can try to construct a top hat wave, which is often very desirable. We're trying to create a spot here that is just nice and square. So these are the desired amplitudes in the receivers for this top hat. Well, again, we don't have enough well-coupled modes to get close to this top hat function. As I said, we see a similar behavior that we saw with the Gaussian, but now for the square or top hat spot. Even going to extremely weakly coupled modes, we do not succeed in achieving a good top hat function at the receiving space, because the edge features are simply too abrupt, even for these very weakly coupled modes. One reason why we must have a strong fall-off in coupling strengths is that there is a powerful underlying sum rule at work here. This sum rule works for both discrete point or waveguide sources and receivers and for continuous functions like wavefronts. This sum rule comes from some very powerful mathematics that we find once we use this singular value decomposition approach to optics. Importantly, this sum rule extends to the situation where we have continuous source functions, like phase fronts, and formally also extends to the case where we're considering mathematically infinitely large basis sets. Such infinite sets are common in problems with continuous functions. Importantly too, even though the sets of functions can be infinite, this sum rule shows that we still only obtain finite numbers of well-coupled channels. This sum rule for wave problems was apparently not known before, so this is a new result in optics, and a very fundamental one. The formal proof of this sum rule requires a branch of mathematics known as functional analysis, which can sometimes be a forbidding subject. I have, however, written a tutorial on that, which you can find at this reference, which hopefully makes this subject somewhat more accessible. Fortunately, though that mathematics can be difficult, there are simple results that give us what we need, especially because the wave coupling operators are all what are called Hilbert-Schmidt operators. Let me try to explain what Hilbert-Schmidt operators are. For some scalar operator g omega here, a Hilbert-Schmidt operator is one for which the integral over the source and receiving volumes, like this here, is a finite number. So the integral of the modulus squared of the operator over the two volumes. This will be true for any wave operator with finite volumes, because finite sources give finite waves. This also extends easily to vector waves, incidentally. A key point here is that all physical wave operators are such Hilbert-Schmidt operators. So we get sum rule results even as we go to continuous functions and to infinite sets. The sum rule is the answer to that integral. This point has not been appreciated in previous discussions of numbers of communications channels. The uniqueness of the communication mode functions and the fundamental Hilbert-Schmidt nature of wave coupling operators, which leads to sum rules, as we've seen from that integral, enforce the inability practically to beat the diffraction limit. And we also have this surprising and as yet unexplained, apparently universal exponential fall-off in coupling strengths beyond the conventional diffraction limit, which is of course consistent with the sum rule. Taken together, these give a very powerful understanding of these limits in optics and in wave systems generally. I'll conclude by showing some references for this talk. The main reference, Waves, Modes, Communications and Optics, covers essentially everything we've been talking about here. Thank you.